Good evening. I welcome you all for the week 11 live interactive session for the course Polymers, Concepts, Properties, Uses and Sustainability. Now, let's get on to the session. As usual, we will have a brief recap of lectures of week 11. I've just shared my screen. So, week 11 lectures were on polymer processing and recycling techniques. So, lecture 78 was on rheology and entanglement. This was a concept based lecture. So, here rheology was introduced, where rheology is nothing but study of deformation behavior of fluids. So, we have a shear based and extensional based rheological studies. And in generally, in these rheological experiments are done for simplicity in one dimension, and also narrow gaps are used and different control variables. Either it can be a stress controlled experiment, strain control, oscillatory experiment, steady shear experiment. And then, but polymer processing involves large deformation and non-linear rheology. And then rheological geometries, the rotational rheometer, uh, thin gap, and then different kind of geometries used in rotational rheometer, cone and plate, parallel plate, concentric cylinder geometry. In which cases each of these geometries are used, and what are the advantages and disadvantages, and what are the type of samples that can be evaluated in these type of geometries were all discussed. This was followed by a discussion on oscillatory shear response of polymer melt and extensional flow response in case of a branch polymer, especially a comparison between HDPE and LDPE, and strain hardening in case of LDPE was discussed. And then, how is the fiber orientation in case of a shear and extensional flow? So, this was also discussed. Next, lecture 79 was on rheological models. This was again on concepts. So, what are the different classes of models? You have linear viscous, non-linear viscous models. Linear viscous, you have your Newton's law of viscosity, where shear stress is directly proportional to shear strain, and the constant of proportionality is your viscosity. In case of non-linear viscous, where you have the generalized Newtonian fluid, you have viscosity replaced by a apparent viscosity, which is not a constant but a function of shear rate itself. Okay, and then linear viscoelastic fluid model was discussed, and then there was a discussion on shear thinning models. Here there was a discussion on Karyo-Yasuda model for polymer melts and polymer solution, and then Herschel-Buckley model, which is nothing but a yield stress fluid model. Next, there was the brief discussion on non-linear viscoelastic model. The Fanthian Tanner model was discussed here. The convected derivatives, frame indifference, and concept of material objectivities, these were all discussed. The next lecture, lecture 80, was on rheology and processing. This was on uses. So mixing in different flows. So in polymers, due to their high viscosity, we have laminar mixing. And how good is the mixing in case of a simple shear flow? And then in case of an extensional flow, and how is the point of separation between 2 points in case of a shear and extensional flow were discussed. The next, viscous dissipation was discussed. And then there was discussion on dye or extrudate swell. So, what are the macromolecular reason behind these extrudate or dye swell? So, stretching and orientation, the recovery, entanglement and reparation. And then, what is the correlation with the rheological properties? So, what is the influence of the normal stress, especially for a dye swell of a polymer extrudate to that of a Newtonian fluid extrudate? A correlation was shown. And then the rheological and interfacial properties, there was a small discussion. Lecture 80, further there was a discussion on deformation in simple shear flow. So here, velocity gradient, strain rate tensor, and stress tensor for Newtonian and generalized Newtonian fluids were discussed. And there was a discussion on stress tensor in simple shear flow for viscous fluids and viscoelastic fluids also. So the total stress tensor, the deviatoric stress tensor, the normal stress difference. For example, in case of Newtonian and generalized Newtonian fluid, you do not find a normal stress difference. The normal stress difference is zero. Whereas when you come to viscoelastic fluids, there is a role of normal stress difference. Okay, so that was discussed. Then different techniques of rheology. So rotational rheometry, tube flows, extensional rheometry, what are the trade tests in rheology? So these were all discussed uh, in lecture 80. Next, in lecture 81 was on absorption and leaching. So this was a lecture on sustainability aspect. So what is the fate and transport of polymers in environment? Because of their low density and longevity, and what is the exchange of small molecules, small molecules taken up by the polymer is absorption, and coming out of the polymer to the external environment, whether it can be another polymer, or it can be a liquid phase, or it can be a gaseous phase like air, or it can be a soil environment. So that is leaching. So what are the thermodynamics of solute exchange? The concept of solubility, partitioning, sorption isotherm, and then kinetics of solute exchange. Okay, these were all discussed. Then there was a discussion on absorption kinetics, especially Fickian, non-Fickian, and case 2 diffusion. And finally, leaching and leaching kinetics were also given an idea. Next, the lecture 82 was on swelling of polymers, which is a property based lecture. So, swelling of cross linked systems. So, what happens if a solvent comes in contact with a linear or branched polymer? So it actually, gets plasticized, and then solubilization starts taking place, and then you end up in a polymer solution. Whereas in case of cross-linked polymers, there is no dissolution of the polymer, but, there is a swelling that takes place uh, upon solvent uptake. Okay, because of the cross-linking present in the polymers. So what is the relation between the osmotic pressure and chain elasticity that plays a vital role in swelling? And then application. So this where are these cross-linked polymers with swelling are used? For example, super absorbent materials which are used in diapers, and then in sanitary napkins. And there are also agricultural applications which, these super absorbents are, uh, uh, put on soil. Okay, so that there is a moisture absorption which supports the crop production. Okay, and then measurement of crosslink density, and then hydrogels and organogels. So hydrogels means the solvent that is taken up by the cross-linked polymer network is water, or aqueous based solvents like your salt solution, whereas organogels means organic solvents. Okay, and then Flory-Huggins theory and network elasticity. So what is how is swelling ratio based on weight and volume? And then osmotic pressure, which can be estimated from change in Gibbs free energy, and the network elasticity based on ideal chain model, which is entropy based. And then how, balance between these two, you can arrive at the Flory-Rayner equation for swelling. Okay, so these were all discussed. And finally, kinetics of swelling. So what are the parameters that play an important role in kinetics of swelling? Mass transfer, the large deformation, the relaxation of polymers. So these concepts were discussed in this lecture. Next, the final lecture of the week was on viscosity for polymer processing, which is again a property based lecture. Okay, so in this lecture, capillary rheometry was discussed. So for Newtonian fluid, you use a Hagen-Poiseuille equation, whereas for a viscoelastic fluid, you do not have the Hagen-Poiseuille equation is not valid for a viscoelastic fluid. So how do you derive relation? So based on equation of motion and shear stress between the polymer and the wall. Okay, and what happens in the developing flow, and the entrance effect. So when you have the entrance effect where the flow is not fully developed, you will have to apply end corrections. For example, Bagley correction can be applied. And then there was a discussion on Maxwell model, where oscillatory shear, oscillatory input of strain rate is given for estimation of the dynamic viscosity and how is the model response. So these were all discussed in this lecture. So that's it with the brief recap of the lectures of week 11. Now let's get on to the practice assignment session. So the first question, in a cone and plate viscometer, the rate of strain is related to the speed of rotation of the cone omega, the unit of which is radian per second, and the angle between the cone and the plate alpha, the unit of which is radian, by the following relation. So this is a GATE 2013 question. So is it related as omega into alpha or omega into cos alpha or alpha by omega or omega by alpha? How is rate of strain, the strain rate related to speed of rotation of the cone and the angle between the cone and the plate? So the answer is, it's actually option D. It is the rate of strain is related as omega by alpha. That is, it is speed of rotation of the cone omega divided by the angle between the cone and the plate alpha. So how can you actually arrive at this, without knowing the background? Just if you know the unit of rate of strain, the unit is second inverse, right? So from the given two parameters, the unit of speed of rotation of the cone omega is radian per second and the angle is radian. So radian per second by radian. So radian gets cancelled. So it is 1 by second, that is second inverse. So you can just straight away arrive at this relation, which is omega by alpha is equal to the rate of strain. Simply by knowing the unit of rate of strain, and if you look at the units of these two parameters, you can arrive at what is the relation. One of the key features of rheometry is narrow or thin gap, making dash as insignificant. So in rheometry, one of the major feature is that using narrow gap between the plates, whether it is going to be cone and plate or parallel plate, whatever it is. So the gaps are very narrow or thin. So why is this narrow gap actually used? Is it to make gravity forces insignificant or pressure forces insignificant or inertial forces insignificant or viscous forces insignificant? Which of these becomes insignificant when you have narrow or thin gap? It is actually the inertial forces. To make the inertial forces insignificant, uh, yeah, you apply, you have a narrow or thin gap. So when you have the force balance equations, in order to cancel out the inertial forces, you have the thin gap or narrow gap. Okay. Now next, perfect fiber orientation can be achieved in dash flow. Can we achieve a good fiber orientation in a shear flow, or can be achieved in an extensional flow, or both in shear and extensional flow, or neither in shear flow nor in extensional flow? Which of these is the right option? So a perfect fiber orientation can be achieved in extensional flow. When you apply an extensional flow, the fiber orientation is better compared to a shear flow. Okay. Next, for Newtonian fluids, the extensional viscosity is related to shear viscosity as, is it related as extensional viscosity is equal to shear viscosity, or extensional viscosity is one third of shear viscosity, or extensional viscosity is three times the shear viscosity, or extensional viscosity is equal to two times the shear viscosity? Answer is the extensional viscosity is 3 times the shear viscosity for Newtonian fluids. This is for Newtonian fluids alone. Okay. Next. Match the following rheometric geometries with features or applications. So the geometries given are cone and plate geometry, concentric cylinder geometry, and parallel plate geometry. And what are the features given here? Low viscosity sample, non-uniform shear strain rates, uniform strain rates, and suitable for phase-like systems. So, which of the geometries can be used for, or which of the geometry are used for these features or application? Answer is cone and plate geometry. It is used for uniform strain rates. Okay, because the velocity increases radially and the gap also increases radially in case of cone and plate geometry. Okay, in concentric cylinders is used for low viscosity sample because low viscosity sample means the torque is very small. Okay, so as the area of contact between the solid and fluid is large, so it can be used for low viscosity samples, concentric cylinders. And finally, parallel plate, you do not have uniform strain rates. Okay, because as we have seen in cone and plate geometry itself, the velocity increases radially. Okay, in case of cone and plate, since due to the conical nature of the top plate, you will have the gap also increasing radially, which matches the velocity increase. Whereas in case of parallel plate, parallel nature means there's velocity increase radially, but there is no, uh, uh, you know, uh, gap increase. It's a uniform gap. So this leads to a non-uniform strain rates, but it is suitable for paste-like systems. For example, in case of cone and plate geometry, we have very small gaps of 50 micron gaps. Uh, you know, uh, Between the cone and the plate. Whereas when it comes to parallel plate geometry, you cannot use that small gaps for a particulate system. Okay, like paste like systems and all, we have considerable sized particles. Okay, but in case of parallel plate geometry, the gap can be some 500 microns to 1 millimeter gap. So this can be used for particulate system. So this now you can get a better picture on seeing this image. Okay. So in case of cone and plate, you have the top plate is conical. So this is the cone angle. So as you can see, along the radius, okay, this is the center portion. So and along the radius, so in the center, the radial velocity is omega, and along the radius, the velocity increases as omega r. And also you can see the gap is increased. So this means so your strain rate or shear rate is nothing but your uh, velocity by gap, right? Velocity is meter per second by gap meter. So you will end up in strain rate as 1 by second inverse, right? So obviously, you can see that as velocity also increases along the radius, the gap is also increasing. So that means if there is a balance, so you can achieve uniform strain rates. Okay. And cylindrical geometry, there is a large, area of contact. So, uh, so it can be used for low viscosity samples. And parallel plate, as you can see here also there will be a velocity increase radially. Okay, but the gap is constant, but this leads to non-uniform strain rates. However, when you take cone and plate, the gap can be this portion, especially the center portion, the gap can be very small of 50 micron or even less than that, 50 micron of order. Whereas if when you have particulate systems, with particles and all, no, then it is the particles of considerable size, then it is difficult to do measurements in cone and plate geometry. Whereas in parallel plate, you can achieve gaps of 500 micron to 1000 microns and all. So here phase like systems can be measured. Okay. And in concentric cylinders, you have a large contact area. So across this, this entire portion of the cylinder, right? This between these two cylinders, this annular space. So there's a large space. So this can, so since the torque associated with the low viscosity sample is very small, the area of contact is required to be large in order to measure the viscosities. Okay, that is why concentric cylinder geometries are used. Next, for yield stress fluid having stresses up to yield stress, what is the type of flow? Identify the type of flow. So for yield stress fluids, if the stress is lower than that of the yield stress, okay, that is up to yield stress, what type of flow can be observed? So for yield stress fluids, up to the yield stress, no flow is observed. So only if the material crosses that yield stress, it starts to flow. So your strain rate is zero if the stress is below the yield stress. Okay. The so this is given by the Herschel-Buckley model. Okay. And the model is given by tau is equal to tau yield plus k into gamma dot power n. So this tau yield should be crossed in order for the material to flow. Okay. So below which the material does not flow. Next, identify the type of flow in rotational rheometers and capillary rheometers. What is the type of flow? So is it Poiseuille flow for rotational rheometer and Couette flow for capillary rheometer, or for both rotational capillary rheometer, is it Couette flow, or is it Couette flow for rotational rheometer and Poiseuille flow for capillary rheometer, or is it Poiseuille flow for both rotational and capillary rheometer? Which of these is correct option? The right answer is, in case of rotational rheometers, okay, for example, we saw in the previous question, a cone and plate or parallel plate geometry. So, in case of cone and plate, the top plate, rotates. Okay, the cone rotates. Uh, as you can see, there is a rotation of the cone because it is attached to the shaft. So, this rotates. Okay, whereas the bottom plate is stationary. This type of flow is called as a Couette flow. The same applies for parallel plate also. If you could see, these are all rotational rheometers. So geometry is used for rotational rheometers. So one of the plates here, this plate is moving, is rotating, whereas this plate is stationary. Similarly, the inner cylinder is rotating, whereas the outer cylinder is stationary. So one of the plates is moving, or one of the cylinders is moving, and the other is stationary, in between which the fluid or the polymeric material is placed. Then the type of flow is called as a cuvette flow. Whereas in case of capillary rheometers, it is called as Poiseuille flow. So in a capillary tube, it is a pressure based flow. So there should be a pressure draw or pressure difference between the two ends so that there is a flow. Okay. So for a rotational rheometer, it is Couette flow, and for capillary rheometer, it is Poiseuille flow. Poiseuille flow is a pressure gradient based flow. Whereas Couette flow is one of the plates moves and the other plate is stationary. So since one of the plate is moving, it will make the fluid closer to it also to move. Okay, and that is how you will have the velocity gradient across the length of the between the plates. Okay. So the fluid close to the bottommost plate will be stationary, whereas the fluid closer to the topmost plate will be moving with closer to the velocity of the top plate. And then there will be a velocity gradient across that direction between the top, across that height, thickness, or gap between the plates. Okay, so that type of flow is Couette flow. Next, identify if the statement is true or false. The expression given below is an example of linear viscoelastic model. So you have this expression as shown here, some constant into tau by x plus lambda 1 into first derivative of your stress rate of change of stress minus uh, your tau y into gamma dot yx minus of lambda into gamma dot yx into tau xx plus tau yy into gamma dot yx is equal to eta naught into gamma dot yx plus eta naught into lambda 2 into uh, rate of change of strain rate. Okay, where this constant is given by exponential of minus some e into lambda 1 by eta naught multiplied by tau xx plus tau yy plus tau zz. There's nothing but the normal stress component of the deviator stress. Okay, so it is not a linear viscoelastic model. So the statement is false. The above expression is an example of non-linear viscoelastic model. Why is it non-linear viscoelastic model? So if you look into the expression, you could see terms which are having product of stress and shear rate, and then in multiple places you could see, and also an exponential term, and this is actually the part of the constant, this c, so which is a exponential term into product of stress. So these all terms imply that it is a non-linear expression, and this expression is actually your Pantheon Tanner model expression. Okay, now next question. The macromolecular scale reason behind development of non-normal stress differences in a viscoelastic fluid under shear is due to equilibrium dash like macromolecules are dash that leads to a tendency of dash. So what is the reason behind, the question is basically what is the reason behind normal stress difference in a viscoelastic fluid? So, what is the structural reason, macromolecular structural reason behind the normal development of normal stress difference in a viscoelastic fluid? So, the answer is, so under equilibrium, under shear, uh, so under equilibrium, generally the macromolecules will have a coil-like structure. So, when shear is applied, so what happens is that the macromolecules are stretched. Okay, so once it is stretched, and again when you start coming back to the equilibrium, there is a recovery associated. Okay, so that is why there is a reason for normal stress differences. Okay, so for example, when the viscoelastic fluid is between two platens, so when you start shearing the fluid, there is a stretching of the coil-like structure, and then there is a tendency to recover back also due to the inherent nature to have to be in a high entropic state. Okay, inherent nature of being in a high entropic state, they try to recover. So this, what happens is that this creates a normal stress and a pushing. So between the plates, the plate is pushed apart. So this is what creates a normal stress difference. Okay, the plates are pushed apart. So there is a perpendicular force that is happening. So in order to maintain the gap constant, since the plates are pushed apart due to the inherent elasticity in the material, so you have to apply a normal stress in order to maintain the gap. Okay, so that is why. So this is the structural reason behind the normal stress difference in a viscoelastic fluid. Okay, next. Identify the different techniques of rheology based on application of pressure from the below set of instruments. So extensional rheometer, U-tube viscometer, rotational rheometer, and capillary rheometer. Which of these are based on pressure based flow? So we have exponential rheometer, U-tube viscometer, rotational rheometer, and capillary rheometer, which are based on pressure-based flow. So the answer is U-tube viscometer and capillary rheometer. We already saw in the previous questions, one of the previous questions, that capillary rheometer are based on Poiseuille flow, which is nothing but the pressure-based flow. So capillary rheometer are based on pressure-based flow, and similarly U-tube viscometer also, it is based on your pressure-based flow. So this is from the lecture. So tube flows or pressure-based or pressure drop versus flow rate. So because of the pressure drop, there is a flow. Okay, in U-tube viscometer, in a Bell-Hurd viscometer and capillary rheometers and all, you have a pressure-based flow. Okay, next. Identify if the statement is true or false. So, huge amount of dissolved organic compounds are leaching from marine plastics. Is it true or is it false? Is there a huge amount of dissolved organic compounds that are leaching from marine plastics? The answer is yes. There is a huge amount of dissolved organic compounds that are leaching from marine plastics. In fact, it is nearly 23,600 tons. It is 23,600 tons. So it is 23,600 into 1000 kgs. Okay. This is based on a paper that was published in 2018. So with that, you know, it says that there is a 23,600 tons of dissolved organic compounds that are leaching. So now we don't know, it's like 2018 means now it's 6 years after that. We don't know whether it has increased or decreased. Whether, because there is a lot of importance given on sustainability. Hopefully it should not have increased to much more extent. At least, if this was maintained or started reducing, that is very good. Okay, but it's a huge amount. We have to be very careful, okay, because it will pollute the marine environment. So this causes, deaths of different types of, marine flora and fauna. Okay, so we have to be very cautious. Next, uptake of solute as a function of time in a polymer film sample is given by mt by m infinity is equal to k absorption into t power n. Okay, the type of diffusion where absorption is a linear function of time is called. So, absorption is going to be a linear function of time. Then what is the type of diffusion called? So, if absorption is a linear function of time, then mt by n infinity is equal to k absorption into t power 1, because it's a linear function of time. That means n should be equal to 1. What type of diffusion is it called in this case? This is called as case 2 diffusion. So here there is a movement of front between glassy or rubbery polymer. So here n is equal to 1. So it's a case 2 diffusion. Movement of front between glassy and rubbery polymer. So the absorption takes place. So the total, this entire film is glassy. So it starts absorbing, the small molecule starts getting absorbed in the, exposed portion. And then that portion gets plasticized and turns rubbery. Okay. And then slowly this rubbery region starts developing. Okay. And this is a linear function of time. That means t power 1. Okay. So this is called as a case 2 diffusion. Okay. When n equal to zero point 0.5, then it is a Fickian diffusion, and n not equal to 0.5, it is called as anomalous diffusion, where diffusion and relaxation both plays a role. And when n equal to 1, this is called as a case 2 diffusion. Okay. Now next, identify the correct relationship for swelling ratio based on volume and polymer fraction. So swelling ratio based on volume is given by SV and polymer fraction is 5p. So what is the relationship between the two? So SV into 5p is equal to 1. or is it SV by 5P is equal to 1, or is it SV minus 5P is equal to 1, or is it SV plus 5P is equal to 1? Which of these is the correct relation? So your swelling ratio based on volume is, it is the volume of swollen polymer by volume of the dried polymer. Alright. So what is the relation? The correct answer is SV into 5P is equal to 1. So we know that SV is equal to, in the spelling ratio based on volume is volume of swollen polymer by volume of dry polymer. So that is nothing but 1 by 5P. So because 5P is your volume fraction of the polymer, right? So volume fraction of the polymer is given by volume of polymer divided by volume of polymer plus volume of solvent. That is nothing but the volume of the swollen sample, correct? So it is nothing but the inverse of the swelling ratio. Okay. Now let's get on to the next question. This is actually a GATE 2014 question. So what is given in this question? The constitutive equation for a shear thinning polymeric fluid is given by sigma is equal to mu naught into gamma dot by 1 plus gamma dot divided by gamma dot naught, where sigma represents shear stress in pascals, gamma dot the corresponding shear rate in second inverse. The quantities mu naught is equal to 20 Pascal seconds and gamma dot naught is equal to 10 second inverse are constants. Find the apparent viscosity of the polymer sample in Pascal seconds when the applied shear rate is 40 second inverse. So what have they given? They have given some relation for a shear thinning polymer fluid between the shear stress and the corresponding shear rate. And they have given the values of some constant, and they have given what is the applied shear rate. They have asked us to find what is the apparent viscosity. Okay. So given sigma is equal to mu naught into gamma dot by 1 plus gamma dot by gamma naught dot. Mu naught is 20 Pascal seconds, gamma dot naught is 10 second inverse and gamma dot is 40 second inverse. So what is apparent viscosity? Apparent viscosity is eta of gamma dot, because it is a viscosity which is a function of shear rate itself, is equal to shear stress divided by corresponding shear rate. Okay. So this is what is given. This applies for a generalized non-Newtonian fluids. So apparent viscosity, you have the relation sigma is equal to eta into gamma dot, where eta is a function of gamma dot itself. Okay. So that means gamma dot is equal to sigma, eta is equal to apparent viscosity is equal to sigma by gamma dot. So we have the relation for sigma, that is nothing but mu naught gamma dot by 1 plus gamma dot by gamma naught dot. So divided by gamma dot. So you will end up with the relation mu naught by 1 plus gamma dot divided by gamma naught dot. So you have the value of mu naught, which is 20, divided by 1 plus gamma dot is 40 second inverse. Gamma naught dot is 10 second inverse. So 20 by 1 plus 40 by 10. So which is 20 by 1 plus 4, which is 20 by 5. You will end up with the apparent viscosity is equal to 4 Pascal seconds. Okay. This is a very simple problem. Next. Identify which type of flow, whether is it shear or extension, that has a better mixing from the below figure. So they have given some figure where they have given some graph. So the graph is area of deformation by area before deformation for a hypothetical sphere. Okay. And the y-axis is specific energy. Okay. And you could see this line is for simple shear, this is for a uniaxial extension, and this is for a planar extension. Okay. Or biaxial extension. Okay. So which one will have a better mixing based on the figure? So you could see that the specific energy increases continuously rapidly in case of simple shear, whereas in case of uniaxial extension and biaxial extension, there is a minor increase and then almost it is getting to a constant value. Okay. So the answer is the extensional flow has better mixing as the energy required for mixing is low compared to the simple shear for a given deformation. So x-axis is deformation, area of deformation by area before deformation, and y-axis is energy. So we see that for simple shear there is a continuous increase and a high increase. Okay. Whereas in case of an extensional flow, in both the cases, whether it is going to be uniaxial or biaxial, the energy required is lesser. So it is increasing initially and then it is a kind of there's a very minor increase and then it okay in both the other extension case. That means the energy required is less, means with that small energy required itself there is a equivalent mixing happening. Okay, because the area of deformation is same in case of both the cases, right? That means shear extensional mixing is better as it requires a lesser energy compared to a shear mixing for same amount of deformation. Okay. Now, so that is what is given here as well. Okay. Next. In the context of polymer swelling, osmotic pressure can be estimated based on what? How can we estimate the osmotic pressure in polymer swelling? So here, osmotic pressure can be measured based on change in Gibbs free energy of mixing with number of moles of solvent. So this is what, so the osmotic pressure is given by change in delta G of mixing with number of moles. So this is nothing but based on the flow reagents theory. So pi is a function of dou delta G mix by dou ns. Okay, this is the expression for that. And from where? From this flow reagents theory based expression for osmotic pressure, which is based on Gibbs free energy of mixing by number of solvents, change in Gibbs free energy with number of solvents, moles, you can arrive at the Flory-Reiner equation, which is a force balance between your osmotic pressure and the network elasticity. Okay. Now next, identify if the statement is true or false. As interaction parameter chi becomes more negative, the swelling ratio decreases. Is it true that when the interaction parameter chi becomes more and more negative, then the swelling ratio is decreasing? So the crossing polymer network is not able to take up more solvent. Is it true? When chi is more negative, it is actually false. So when chi is more negative, interactions are more favorable. When chi is more and more negative, there is much more attraction between the solvent and the polymer. Okay, so that means when there is a more attraction, then there is more take up of solvent by the polymer. That means the swelling is more. That means as chi becomes more and more negative, higher and higher swelling ratios can be obtained. So more and more better interaction between the solvent and the polymer, more attraction between the solvent and polymer. So a polymer is able to cross-link polymer network is able to take up the solvent more. So it swells more. Okay. So you could see chi. So as it becomes more and more negative, so minus this chi value, it becomes positive. So your SV becomes more and more higher value. Okay. Because here 1 minus chi. So that means if chi value is negative, minus of minus will become plus. So this whole value will be increasing a lot. Okay. Next. For a viscoelastic fluid, the relation based on balance of linear momentum is used in capillary rheometer, where the relationship is given as, is it given as tau r z is equal to small r by capital R into tau r, or is it tau r z is equal to small r by capital R tau r, or is it tau r z is equal to R into delta P by 2L, or is it tau RZ is equal to capital R by small r into tau R. Which of these is a valid expression for the shear stress with respect to the wall shear or with respect to pressure gradient, uh, which can be derived for a capillary rheometer based on a linear momentum balance. So capillary rheometer, for a viscoelastic fluid, you cannot use a Hagen-Poiseuille equation. So you derive the expression based on your relation between the wall shear stress. Okay. So how is that? Based on the linear momentum balance at wall. Okay. And wall shear stress, you use it. So how is the relation? So two options are right in this case. Option A, shear stress tau RZ is equal to small r by capital R into tau R. Also option C, tau RZ is equal to R into delta P by 2L. How is it? So overall stress in the material is a linear function of shear stress at the wall. Okay, this is how the relationship is. Because you could see it's a linear relationship. So it is some multiplication factor with the wall shear stress, which is tau R. Okay, overall stress. Now you have the linear momentum balance. So at the wall, you have the linear momentum balance between the wall shear stress and the pressure gradient. Okay, so the wall shear stress is across the wall, so it is multiplied by 2 pi RL. Okay, and your pressure is valid in the cross section. That means it is the area of the circle, which is pi r square, right? This is surface area of the cylinder 2 pi RL, and this is the area of the circle pi r square. So 2 pi RL into tau R is equal to delta P into pi r square. This is the force balance at the wall. So if you do the mathematics, so your pi and pi gets cancelled, one R and R gets cancelled. So what you will end up, tau R is equal to R by 2 into delta P by L, right? So there is a linear relationship between the overall stress and the stress at the wall, okay, which is given by this expression, small r, that is the radius at any point by the radius at the wall, right? The complete radius into tau r. Okay, so now how do we arrive at the expression C is that you have the tau r expression. So when you apply this tau r into this expression, that is small r by capital R into tau r. So small r by capital R into capital R by 2 into delta P by L. So your capital R gets cancelled. You will end up with tau R Z is equal to small r into delta P by 2L. That is how you will arrive at the expression C. Okay. Now, next. Cox-Mears rule relates complex viscosity to complex modulus. Uh, Sorry, there is a typo error. It's not complex viscosity to complex modulus, but it's complex viscosity to your steady shear viscosity in polymers. Sorry. Cox-Mears rule relates complex viscosity to complex modulus in polymers. Is this statement true? Does it relate complex viscosity to complex modulus? Actually, I told the answer. So does Cox-Mears rule relates complex viscosity to complex modulus in polymers? Is this statement true? The statement is false. I already told Cox-Mears rules predicts complex viscosity and steady shear viscosity are equivalent when angular frequency is equal to steady shear rate. Okay. So Cox-Mears rule, if the material follows the Cox-Mears rule, so steady shear viscosity based on shear rate, okay, increasing shear rate, you will get the steady shear viscosity, okay. It is gamma dot versus eta. You will plot. And your complex viscosity, especially the eta prime versus omega, if you plot, if both these eta versus gamma and eta prime versus omega, they fall on the same points, okay, the same line, then Coxmer's rule is applied. That means the material follows Coxmer's rules. So if the material follows Coxmer's rules, then it is a simple material. Okay, it's not very complex. Okay, so this is what is a set statement. Coxmer's rule predicts complex viscosity and steady shear viscosity are equivalent when angular frequency is equal to steady shear rate. Okay, so that's it with the practice assignment session. So let's also see some questions posted in the forum in July-November 2022 session. So one of the question posted was, mixing of polymer with another polymer is called polymer blend, right? And mixing of individual materials is called composite. Such a way that can we say all polymer blend is a composite? So a student named Uday Kumar has asked, mixing of polymer with another polymer is called polymer blend. Mixing of individual materials is called composite. So such way that can we say all polymer blend as composite? This is what the person has asked. So the answer given by the professor is that polymer blend is mixing of two different polymers. Even under the polymer blends, mixing of two immiscible polymers using compatibilizer is classified separately as polymer alloys. Okay, so immiscible polymers, if they are blended together using a compatibilizer, it is called polymer alloys, even in under blend. Okay, so polymer composite is mixing of polymers with completely different class of materials like glass fibers, carbon nanotubes, carbon fibers. Okay, so it's ideal that we do not confuse these different systems. Okay, so you cannot say polymer blend is composite and all. We shouldn't confuse between this. Polymer blend is in mixing of two different polymers, and even in that polymer blend, if you have two immiscible polymers that are blended together using a compatibilizer, it is classified separately as polymer alloys. So that is again a separate classification. So, and polymer composite is mixing polymer with a different class of material like glass fibers, carbon fibers, okay, carbon particles, carbon nanotubes, graphene graphene sheets. Okay, so it's ideally better not to confuse different systems. Okay, graphene nanoplates or platelets or okay, graphene sheets or carbon nanotubes. Okay, so this is two different system, polymer and a completely different system, that is a composite. Okay, so it's better not to confuse between different systems. Next, actually question is what is happening in this video at 4 minutes 16 seconds. Okay, sir, by observation it is understood that you are explaining the concept by drawing a plot. Drawn plot is not visible. Okay, so this was question posted by Shivakumar. So if you see in this lecture, I think lecture 80, rheology and processing, this portion of the figure image was not visible. This portion was not visible during uh, the video. Okay, but when you download the lecture notes, you could see this actually. So it is shown that in shear flow, actually when 2 points, there is a linear separation. So the two material points separates linearly. That is what is shown here. Okay, there is a linear separation between 2 points. Okay, the points are not separated that much over a period of time, but there's a linear relation in the separation. Whereas in extensional flow, the 2 points are the separation between 2 points is exponential with time. Here, because your velocity is a function of shear rate into your distance. So velocity is nothing but rate of change of displacement, right? So dou x by dou t in is equal to your shear rate into x. So if you just bring the x terms one side and this t in the other side, you have dx by x is equal to shear rate into dt. So if you integrate this, you will get x is equal to exponential of your shear rate into time. So there is a exponential separation in case of your uh, extensional flow. So this is what is a figure that was not visible in the video, but it is visible. It is, you can see this in the lecture PDF. Okay. So this separation is what shown. So these, the in between space comes together, and these points start separating exponentially in case of extensional flow. Okay. So that's it with the session. Hope you all had a good idea of the problems that was discussed and the brief recap of the lectures. So that's it with the session. So in case you have any further doubts, you can post it in the forum. Okay. Or you can also ask in the next live session as well. Okay. Thank you all.